Hello! Welcome to this new unit on complex numbers. In this unit, simply, our goal is to calculate arguments of complex numbers. We already saw the formula in the previous unit. It was a bit abstract. Let's try to make it concrete with practical examples. The requirements are the same as we saw in the previous unit. We will try to explain a little bit the angles that we use, but it is very important to know the angles in radians and in degrees. Okay, here we go. First example, we are going to calculate the argument of a very simple complex number, which is 1 plus 0i. Remember that the formula was arguments equal to the arctangent of the imaginary part divided by the real part. In this case, we can see that the imaginary part is 0 and the real part is 1. Therefore, arctangent of 0 divided by 1 is arctangent of 0, which if we calculate it on a calculator will give us the result 0. Is it necessary to apply the formula in this case? No, not at all. Notice where the complex number 1 plus 0 is located, and as we can see, it is on the real axis. What angle does this complex number form with respect to the real axis? 0. So, you could have calculated the argument directly by saying that it is 0 without applying the formula. Well, now let's take the opposite. Notice now that the complex number is minus 1 plus 0i. In this case, if we apply the formula, alpha would be the arctangent of the imaginary part, that is 0, divided by the real part, that is minus 1. 0 divided by minus 1 is 0, and we could conclude that the argument is 0, but it is not. Be very careful. Here comes into play the part that we have to know where the complex number is. Notice. Actually, the argument is pi. Let's check it. Notice. In the graph, if we represent the complex number, it is at minus 1 plus 0i. That is, it is on the real axis, but in the negative part. Conclusion. What angle does this complex number form with respect to the real axis? Very easy. An angle of pi radians. Well then, as a conclusion, we can deduce the following. If we have complex numbers of the form a plus 0i, actually the value of a doesn't matter to me. A plus 0i. The argument would be 0 if a is positive, or pi if a is negative. So we are going to save ourselves many times calculating the arguments of this type of complex numbers, which actually, if we look at it, since the imaginary part is 0, they are real numbers. Well, another example. Let us now suppose that the complex is 0 plus I. That is, it has no real part, but it does have an imaginary part. What angle does it form with respect to the real axis? Very easy. The answer is almost immediate. If we apply the arctangent definition, it would be arctangent of the imaginary part divided by the real part. We would have infinite arctangent, which would be pi halves. Well, if we draw it, it is much easier to see what the argument is directly on the graph than to calculate it. Notice where the complex number is located. It is 0 plus I. That is, it is 0 units on the real axis, 1 unit on the imaginary axis. What angle does it make with respect to the real axis? 90 degrees, but we're always going to treat it in radians, so we'll say it's pi halves. Now next, what happens if instead of taking that complex number, we take the conjugate, the opposite, that in this case they coincide? Well, it would be, to apply the formula again, it would be, in this case, minus 1 divided by 0. In this case, it would be arctangent minus infinity, which would be pi halves plus pi. How do we get this, or what is the same, 3 pi halves? How do we get this angle? Very easy. Look at where this complex number is represented. In this case, that's the complex number. It's on the imaginary axis, but on the negative side. What angle does it make with respect to the real axis? Very easy. 270 degrees, which is the same, 3 pi halves. We could have answered this to the question of what is the argument of this complex number, or we could have taken the negative and said that the argument is minus pi halves. Well, conclusion. What happens when we have complex numbers of the form 0 plus bi, that is, pure imaginary numbers? In this case, we have that the argument is p halves if the imaginary part is positive, and we have that the argument is minus p halves or 3 p halves if the imaginary part is negative. Well, let's now calculate the argument of a complex number in which both parts are non-zero. Both the real part and the imaginary part are non-zero. Since we have taken a very simple example, 1 plus I, well, in this case, the argument is defined as the arctangent of the imaginary part, which is 1 divided by the real part, which is 1. If you look at it, it's an arctangent of 1, which is pi quarters. Well, or what is the same, 45 degrees? In this case, where is this complex number represented? It is 1 unit of the real axis and 1 unit of the imaginary axis. There we have the complex number. In this case, that angle is pi quarters. It's in the first quadrant, no problem. But what happens if we have taken the opposite of the previous complex number, that is minus 1 minus I? In this case, if we look at it, when we apply the formula arctangent of the imaginary part divided by the real part, we have that it is arctangent of -1 divided by -1. If we now simplify and say that it is arctangent of 1, we can make the mistake of saying that it is simply pi quarters, and be very careful. It is not only pi quarters, we are in the third quadrant. I do not know if you remember the previous unit. Conclusion, we would have to add pi to get the argument. If we represent it graphically, you can see it clearly. This is the complex number that we're working on now, and the argument is not pi quarters, it's 5 pi quarters. Okay, conclusion. Is there a slightly more mechanical way to calculate it without having to plot it? Yes, there is. We would prefer that you don't do that you represent first, or try to visualize where the complex number is before you apply a formula mechanically, because it's easier to get it wrong with a formula than not representing the complex numbers. If we look at it, how can we have summarized all this? If we want to calculate the argument of a complex number, we can calculate the arctangent of the absolute value of the imaginary part divided by the absolute value of the real part. So we forget about the signs, and then we'll find where the complex number is. Well, if we calculate that alpha as the arctangent of the absolute value of b divided by the absolute value of a, what we have to do is to follow the following rule. If the complex number is in the first quadrant, then the argument of z is exactly the value we have obtained. On the other hand, if the complex number is in the second quadrant, that is, the real part is negative and the imaginary part is positive, in this case we should do the following. Once calculated the arctangent, as indicated in the presentation, calculate pi minus the value obtained, then it would give us the argument in the second quadrant. If, on the other hand, the complex number is in the third quadrant, the same thing, we apply the formula, we obtain the value of alpha, and what we would do would be to calculate pi plus alpha or alpha minus pi if we want the angle positive or negative. Well, and finally, if it is in the fourth quadrant, remember that this is simply the last quadrant. It is the positive real part, the negative imaginary part. In this case, once applied the formula of the arctangent of the modulus of b divided by the module of a, you would have to calculate 2 pi minus alpha, the value obtained, or simply put the value obtained with a minus in front, which is minus alpha. This way you can calculate the arguments in a simple and very mechanical way, although I insist we prefer that you represent the complex numbers and deduce which is its argument. Well, remember that there is not only one argument of a complex number, there are infinite arguments for each value of z. Okay, how is it calculated? Very simple. Once the argument is calculated, we would simply have to add 2k pi, where k is an integer value, either positive or negative. The argument of a complex number that lies between the interval minus pi and pi is called the principal argument of z, and is usually denoted as the argument of z. Note that this definition is important. As an exercise, you could review the unit and look for those arguments that we have calculated that are really principal, that is, that are between minus pi and pi. Notice that between minus pi and pi, there will only be one argument. Well, as a review, what would interest me to have understood this unit? Well, how to calculate the arguments of a complex number and to know a little better the complex plane. Finally, I am going to leave you with a couple of exercises that we will solve in the next unit. It would be to try to calculate the argument of these two complex numbers. They are very simple, and I think you should have no problem to calculate them. In the next unit, we will give you the solution and we will detail it step by step. But for now, try it. Thank you very much.